In the previous video, we have discussed about linear regression. We have seen simple and multiple linear regressions. In this video, we will discuss about various regularizers which constrain the output W. So this was the basic model. Y is equal to capital X W plus epsilon, where X is the matrix, Y is the vector, W is the unknown vector, and epsilon is the error. This epsilon error is between Y and Y cap, where Y cap is the predicted output and Y is the actual output. We have seen that the solution to the linear regression problem is a least square solution, and this was the least square solution which we have seen in the previous videos. So in this video we will see what is problems with the ordinary least square and how we can mitigate by using various regularizers like ridge, lasso, and elastic net regression. So the problems with ordinary least square is the multicollinearity. Whenever we have dependent columns, our matrix becomes nearly singular, and it becomes difficult to find the inverse of X transpose X. And also the weight vectors which will be resulted from the least square solution sometimes has a lot of variance. Values can be very high, and that is one of the bigger problem in OLS. And we have overfitting problem and also the unstable inverse whenever the matrix X transpose X is ill conditioned. So in order to solve these problems, we have various regularizers, and we'll see each of those, and we will also see one problem on each of these, and we will also implement in Python and see the result. Before we start the regularizers, let us see some definitions of norms. The general LP norm is defined as follows, where we take the absolute of each element, take power of p, and also the whole all sum it, and take once again the power of 1 by p. So this is how LP norm is defined, and L2 norm can be obtained by substituting p is equal to 2 in the above expression, and the same thing goes with L1 norm, and L infinity norm would be the maximum among all the elements. It is because when you take the power as p, the element which is maximum will max out, and rest all becomes smaller as compared to that maximum element. So L infinity norm would be the max of the absolute of the values, and L0 norm would give the number of non-zero elements in the W vector. Now let us see how these norms can be used to constrain our unknown vector W and obtain the solution. So among the various ways of constraining W, we have three important ones which we are going to discuss here. The first one is ridge regression, where we have the similar kind of minimization problem like the ordinary least square, but we have an extra term, and this extra term is called as regularizer, which is going to constrain the weight vector. And this regularization, as you can see, it is a L2 norm of the weight vector. So the good thing about this L2 norm is it is going to constrain the weight values, thereby the individual elements doesn't go into extreme values. It avoids having large values in the W vector. So this is first a regression called as ridge regression, where we use L2 norm as a regularizer, and the second one is the lasso regression, where we use L1 norm to constrain our W vector. And the advantage of using an L1 norm as a regularizer is that our number of non-zero elements become minimal, thereby it allows us to choose feature selection. It can be used for feature selection. Third way of doing regularization is called as elastic net regression, where we have both L1 norm and L2 norm applied on the weight vector W, and there are two constants, lambda 1 and lambda 2. Appropriately weighing the lambda 1 and lambda 2 will emphasize one particular norm. If lambda 1 is high, the sparsity would be high, and if lambda 2 is high, the L2 norm would be high, and thereby it constrains the weight values. So that's how you can control both L1 and L2 norms in a single minimization problem. So elastic net is about applying both L1 norm and L2 norm. So in summary, we have L2 norm regularizer which gives us minimum norm solution where weight values are not large, and L1 norm regularizer which will result in a sparse solution with the least number of non-zero elements, and elastic net gives a combination of both by appropriately weighting lambda 1 and lambda 2. Let us see more details about L2 regularizer based ridge regression. As I said earlier, we will be using L2 norm on the W vector to constrain the weight vector, and this can be geometrically viewed as a circle equation. As you can see here, if we have W vector of only two elements, W0 and W1, this will form the circle equation. So what we are essentially doing is, by applying a regularizer, we are trying to constrain the weight vectors to a certain boundary. And if we extend the same idea to 3 dimensions where we have W0, W1 and W2, our weight vector would be constrained to a particular sphere, and the same thing can be extended for more than 2 dimensions and 3 dimensions, and you could have a hypersphere kind of a thing where we constrain our weight vector to that hypersphere. So if we try to solve this problem, we get a solution something as follows. We'll be deriving this equation for ridge regression, and we will see how we can solve it. So it is also dependent on this parameter called as lambda, which we carefully choose and thereby weigh how much the impact of regularizer should be there and how much the minimization should be there. So we kind of trade off these based upon this lambda value. If you choose a higher lambda value there, the constraining on the weight vector would be weighed more, whereas minimization would be weighed less. So in this way, we try to obtain the weight vector which not only minimizes the objective function, which is y minus x w L2 norm, and also constrain the weight vector. So this is the solution for ridge regression, and as I said earlier, it penalizes the large weights. So we will avoid, in the result, we will not have large weights. We will have weights to over a particular, constraining to a particular value. And it's important to note that x transpose x plus lambda is always invertible for lambda greater than 0. So that was not the case in OLS, ordinary least square. We used to have situations where x transpose x becomes either ill conditioned or singular, which is a problem, whereas here we don't have that problem, because if you choose lambda greater than 0, this is always invertible. So let's see some more details. Let's now try to derive the ridge regression solutions. If we expand this L2 norm, y minus xw L2 norm, we have something as follows, and the same thing for WL2 norm. And when we multiply it and differentiate and compute the gradient with respect to W, we have something as follows, and when you expand it and turn to the other side, we get x transpose x plus lambda I into W is equal to x transpose y, and W is equal to x transpose x plus lambda I whole inverse x transpose y. So this is the ridge regression solution, and the usefulness of this solution is our weight vector is constrained, and therefore we don't see any large values. Towards the end of this video, I'll be showing a demonstration with a Python code and show you how OLS gives large values for especially for ill-conditioned matrices, and whereas ridge regression try to constrain those and results the solution. So let's see that towards the end. Now let's go to the other geometric interpretation is this problem of using a L2 norm as a regularizer in the objective function is equivalent to the following optimization problem, where we minimize this function subject to the condition that the weight vector is constrained by some value. L2 norm of the weight vector is constrained by some value. These optimization problems are equal, and that's how our weight is getting constrained to a particular circle or a sphere or a hypersphere. So now let us see. So now let us see how Lasso regression works. As I said earlier, in Lasso we will be using L1 norm as the regularizer, and the other objective function is exactly similar. And what does Lasso does is it makes sure that the W has minimum number of non-zero elements or a sparse solution, and Lasso stands for least absolute shrinkage and selection operator, and it introduces L1 penalty. As we have seen, it shrinks quotients, it forces some quotients exactly to 0 and performs automatic feature selection. And the important thing is this is not a convex function because it involves absolute functions, and so therefore we cannot find a closed form solution. We have to use optimization solvers to solve the solution for this. So when you go to the higher dimensions, you will have something called as an octahedron kind of a constraint on the weight vectors, just like in the previous where we had circle and sphere. Here we have a diamond shape, and we have octahedron kind of a shape for W for 3-dimensional W vector. When you go to the higher dimension, you will have an hyper diamond kind of a shapes which constrains the weight vector. So this is a Lasso regression where we are using L1 norm as a regularizer. And so that's what I have been saying. In 2D we have diamond shaped constraint, and in 3D we have octahedral as the feasible region. So let us see what is the geometric equivalent. So as I said earlier, just like previous problem, this particular optimization problem is equivalent to this problem, and both results in similar solutions. So this is more visualizable, more understandable, as this is a minimization problem and we are constraining the weight vector through its L1 norm by a certain value. So thereby we are making sure that when you compute the L1 norm, it is constrained by a particular value. So this is how L1 norm Lasso regression works, and thereby we obtain a sparse solution. So let us see more details on elastic net regression. As discussed earlier, it is a mixture of both L1 norm and L2 norm, and lambda 1 and lambda 2 are the parameters which are used to weigh the appropriate norm. So in if you see the constraint in terms of visualization, L2 norm represents the circle, and L1 norm represents this diamond shaped, and the elastic net represent the blue color arcs which are between the diamond shape and the circle. As you can see, there is a slight curvature at the axis, and also it changes based upon the lambda 1 and lambda 2 values. So in practice, in machine learning using skline library, when we implement elastic net function, we have something like this, slightly different from the equation given here. We choose appropriately alpha and L1 ratio to appropriately weigh the sparsity and L2 norm. So the elastic net, the advantages is it also shrinks quotients, and it also selects features. It handles correlated features better than Lasso, and elastic net should be used when there are highly correlated features, and when you need both sparsity and stability, and also it gives a generalized or a general purpose regularized regression. So I think before we go to the practical implementation, we'll see one problem. Let us consider these 2 points with two values, two data points, and where x1 comma x2 is 1 comma 1 and 2 comma 2, and the corresponding y, which is a dependent variable, is 2 comma 4. When you represent in the form of matrix, you can see something like this, and we want to find out the weight vector w0, w1 and w2, and we will see all the methods here. Let's find first with the ridge based method, or first let's see with the ordinary least square solution. So when we don't have any regularizer, we are just minimizing the y minus xw, and since it is an underdetermined system of equations, and you also have a dependent vectors 1 2 or 2, there are two vectors which are dependent, so it is a rank deficient matrix, and therefore you will be having infinite solution if this y is in the span of x, and we can clearly see this y is in the span of x. So definitely it will have an infinite solutions, and the solutions are represented as follows. So by choosing appropriate t values, we get as many solutions as possible. So now let us see how we can apply ridge regression or L2 norm as a constraint, and see what sort of output we get it. So when you apply L2 norm as an constraint, we can compute the x transpose x plus lambda I. So we will be using this relation which was part of our ridge regression derivation. So let's see when we compute these values x transpose x plus lambda I, so we get these three equations, equation 1 2 and 3, and when we subtract equation 2 and 3, we get something like this, and we finally get w1 is equal to w2. Because we know that lambda is greater than 0, it cannot be equal to 0, and the only way this can become 0 is w1 equal to w2. So when you substitute this and further solve this equation, we get as follows, where we are assuming w1 and w2 is equal to a, and when we substitute, we get these two equations, and finally we compute w naught, which will be 6 minus 6a by 2 plus lambda. So finally, after substituting equation 6 in equation 5, we get, and after simplifying, we get something as follows, and finally when you write the ridge regression solution, you will have something as follows. So what we can observe is when lambda tends to 0, our ridge regression solution will become 0 1 1, and this is a minimum norm solution, and thereby we are able to nicely restrict the weight values. When we implement in the Python, we will clearly see the effect of it, what sort of solution we get for OLS and what sort of solution we get for ridge regression. So now let us see how what sort of solution we have for L1 norm based lasso regression. As you can see, it results in a sparse solution, and this cannot be solved using any closed form formula, but we have to use optimization solvers to solve it. So we get one of these solution. As you can see, the weight vectors, we did not constrain the L2 norm based weight, so the values are slightly higher, but you can see a sparse solution in L1 based lasso regression. And finally, for the elastic net, we have these three conditions. When lambda 1 equal to 0, so this becomes 0, it becomes same as L2 norm based ridge regression, so you get ridge kind of a solution. When lambda 1 greater than 0 and lambda 2 greater than 0, you get a solution 0 comma a, which means there is some amount of sparsity, you got it, and also you are able to constrain the values of w. And finally, when lambda 1 is very large, which means when you have sparsity imposed very much, so you get a more sparse kind of a solution. So finally, by applying ridge regression, we are able to reduce the quotient magnitude but keep all features, whereas by using lasso regression, which is an L1 norm based regularizer, which results in a sparse solution, thereby we are able to select the important features, and elastic net is able to handle both, and it is also helping in both selecting features while handling correlations. So now let us see how we can implement these in Python and see the results of W vector. So now let us see the Python based implementation of all these regularizers. Here we have taken a slightly an ill-conditioned matrix just to demonstrate the usefulness of L2 and L1 regularizers. So when we have chosen such a matrix, this is very ill-conditioned, and also we have dependent columns. So when you compute the OLS, which is ordinary least square solutions, we will be having something as follows. And here, as you can see, we are using NumPy library and linalg and P inverse, which is pseudo inverse, and we are using the Y vector. So when you compute it, as you can see, the W values are very high. Okay, if you have taken a normal matrix, we would get normal values, but just to demonstrate how L2 regularizer works, we have taken an ill conditioned matrix and we are able to get so high values for W vector in the case of ordinary least square solution. So now when we apply L2 regularizer, we have this is as you can see, x transpose x lambda I, and we are taking the pseudo inverse of it and computing the multiplying with the x transpose y. So this is a regularized ridge regression based solution, and if you see the solution of the ridge regression, weight values have been constrained very much. So our weight values are within the limits, and that's the usefulness of ridge regression. And when it comes to the Lasso, which is an L1 norm based regularizer, we have Lasso as a function in sklearn. As you know, we don't have a closed form solution for Lasso regression. We have to use optimization solvers. So sklearn provides this Lasso method, and we have used the alpha value as 0.1. Alpha, you can call it as lambda, one of those, both are same, and we are able to get the sparse solution, which means least number of non-zero values, and majority of the values are stringed or directed towards 0. And finally, the elastic net. Once again, we have a method called elastic net in sklearn, and we use it, and we can see here, when we use alpha is equal to 1, when alpha is 1 and L1 ratio is 1, so this 1 minus 1 is 0, so this whole term will go, L2 norm will go, and we will only be left with L1 norm, and therefore you are resulting in a sparse solution. So in this way, you can change the weights and appropriately obtain the solution for various regularizers in Python.